Today's video focuses on hypothesis test for a population mean. Remember what the fundamental idea behind a hypothesis test is. We reject the null hypothesis if the observed sample is very unlikely to occur if HO is true. So we usually reject when we have a really low p-value such as 0. I want to first talk about the differences between hypothesis testing for population proportions and population means. Essentially, these two things are very similar. A hypothesis test is a hypothesis test. The only difference is what we are studying. So there are three key differences. The first is the population of interest. For proportions, the population of interest is usually some percentage. We say P equals a proportion of something or a percentage of something. Whereas for means, the focus is going to be on the population of interest variable mu, which is the mean of something or the average of something. So we first need to know the population of interest. Again, that's why we talk about it. The second difference is in the conditions. The conditions are actually the same for population means as they are for proportions. Random, large, and less than 10% of the population. The sample size. The key difference between a proportion and a mean lies in how we determine if something is large, which is similar to when we did a confidence interval. So remember, proportions is n times p, and n times 1 minus p is greater than or equal to 10. But for means, we have to follow the central limit theorem, commonly referred to as CLT. And that's the sample size is greater than or equal to 30. The third difference and final difference between the two is this test statistic that we're talking about. So for proportions, the test statistic is always Z. Think of proportions, the proportion standard deviation, as a way to always know how to find a standard deviation. It's always known. Okay? So since we can always find a standard deviation for proportions, the population standard deviation, then we use only Z. But for means, and we talked about this again with confidence intervals, we have to use either Z when the population standard deviation is known, or our new test statistic T when the population standard deviation is unknown. That's an or. I will admittedly say for most mean tests, we use the test statistic T, but that does not mean we don't use Z. So let's review the assumptions for a confidence interval for a population mean. The first one is that the sample mean, X is the sample mean from a random sample. Again, that's similar to proportions. The second is the sample size is N is large, N is greater than or equal to 30, the central limit theorem, or the population distribution is normal. If we don't know that if the sample size is not large, or we don't know the population standard deviation distribution, then we graph our data when neither is true. If our data is approximately normal, then we can proceed. And the last and final thing is the sample size is less than 10% of the population size. So we're now ready to do a full docs here. A study conducted by researchers at Pennsylvania State University investigated whether time perception, an indication of a person's ability to concentrate, is impaired during nicotine withdrawal. After a 24-hour smoking abstinence, 20 smokers were asked to estimate how much time had elapsed during a 45-second period. Researchers wanted to see whether smoking abstinence had a negative impact on time perception, causing elapsed time to be overestimated. Suppose the resulting data on perceived elapsed time were as follows. So this is our sample data. Is there significant evidence to suggest smoking abstinence had a negative impact on time perception? So, first, we need to know what the population of interest is. So mu is equal to the average time the smokers believe elapsed during a 45-second time period. So, what is our null hypothesis? Our null hypothesis is that mu is equal to 45 seconds. Our alternative is that we believe that they're going to overestimate the time, so more than 45 seconds. Since this is not a intense study, we can make our significance level at the 5% level instead of really low. A type 1 error here wouldn't be terrible, but we don't want to overestimate a type 2 error. So we can make it about 5%. Okay? Now we're ready for outline. Sorry, the significance level can go in outline. Now the conditions. So I believe we will have to assume whether or not the sample is random. So we're going to assume the mean comes from a random sample. The second test here is whether it's large. Well, n equals 20, so it's not large enough, and we know nothing about the population distribution. So we need to graph this. I'm going to create a box plot. So I'm going to get my 5-number summary. And now I have enough information to create my box plot. So let's create the box plot just to see if it's normal enough. 30, 40, 50, 60, 70. So my minimum is 39, my Q1 is 52, my Q3 is 68, so 52 to 68, 52 to 68, 39, 73 was my maximum, I believe, and my median is 58. So this is time perceived. Based on this box plot, the data does look approximately normal. Therefore, I can proceed. So number 3, n is less than 10% of students at Penn State. Okay, so now we're on to compute. So because the population standard deviation is unknown, I'm going to use my t-statistic, which is my sample mean minus my hypothesized value over the standard deviation times the square root of the sample size. So I need to find my sample mean and my sample standard deviation. Well, I already did a 5-number summary, so it's available right there. My sample mean is 59.3, and my sample standard deviation is 9.84. X bar equals 59.3, and SX equals 9.84. So I do my t-test here, 59.3 minus 45 over 9.84 divided by the square root of 20. going to pause the video here just to do the calculation real quick. So I calculated it, the test statistic, and I got 6.50. So T is equal to 6.50. Since I'm doing a t-test, I have to know what the degrees of freedom is. The degrees of freedom is equal to 19. Remember, it's n minus 1. So here's how you look for the p-value with a chart. What you do is you go to the degrees of freedom, which is 19, and then inside the degrees of freedom, you have to look through the row until you find your test statistic. Notice that the highest it goes here is 3.883. So if I look up at the very top here, then I'll see that the p-values are located at the top. The p-value for the highest value on this chart is 0.0005. Since my number is well above that, I can assume my p-value is approximately 0. So, to end, what's our solution? Well, first we have to reject the null hypothesis. Our p-value is less than our significance level. Therefore, we have convincing evidence that we have significant evidence that smoking abstinence go back to my question just to make it very direct. There we go. We have significant evidence. Oops, can't forget that word. That's the most important word in statistics. We have significant evidence that smoking abstinence had a negative impact on time perception, causing elapsed time to be overestimated. That's all I got.